But besides being tedious, is it easy, difficult, annoying, frustrating?
Java is frustrating.
Yeah. Okay.
But other than that, it's great.
So I'm trying to get out of the weeds here a little bit and understand what this does for us in the engineering context, right?
Sorry?
So in the engineering context, what does this do for us?
Uh-huh.
Right? So if I understand this correctly, as long as we implement coalgebra and algebra, we have kind of for free a way to transform recursively from type to type.
Exactly.
Spark to Avro, right?
Yeah, maybe I should have made a slide about that, but later, for now, we are focusing on the Parquet flavor of schemas. Afterward, we'll focus on the Avro flavor of schemas. And using that, you can, for free, without writing new function, go from an Avro schema to a Parquet schema, back and forth, for free. Because you use the coalgebra to go from Avro to schema F, and then the other algebra to go from schema F to Parquet. But you've already written these algebras and coalgebra, so it's for free. And if you have much more flavors of schemas, you will be able to freely convert back and forth. So this is a bonus, but it's cool. That's not why we use that, we write that in the first place. We just want to be able to manipulate schemas of different flavors. But for free, we gain the ability to go from one flavor to another without thinking about it.
The thing is that since you're talking mainly about algebras and true algebras, well, you can compose them. You can way more easily compose recursions using recursion schemes, where, for example, the ILO is both algebras and co-algebras. So if you got one transformation that will go from the schema F to Spark, or from Spark to a schema F, and then from a schema F to Avro, then it's not exactly going to be two recursions, two traversals. It's going to be done way more efficiently at the same time, because the only thing that you define are those algebras and co-algebras that do not, they don't do themselves the recursion. They just define the logic.
Right.
So you can reuse that logic and compose them and create. You can even go further and do algebra transformations, but we're not going to go into that. But
Maybe not.
So you can do transitive kind of schema.
Yeah.
Right? If you can get A to B, B to C.
yeah,
Exactly.
but not transitive in terms of first I do the first recursion and then I do the other one. You see what I mean?
Yeah.
It happens at the same time.
You compose the algebras, and when you compose them using high-low, as I said with the diagram, you never build the whole tree in memory. So you're really, really efficient. So you start from, say, a Parquet schema, you go down one branch, and then you go up that branch, already building, say, the Avro schema. You never build the whole schema F tree, so it's efficient and it's for free. And on a strictly engineering point of view, it's much more easy to test these kind of functions, which are pure functions, really simple, just a pattern match.
And they're not tied to the structure.
Yeah, so you can test in isolation, you can compose them, you're in heaven.
Is this kind of how like the code generator in Ubi works, like the macros in Ubi?
I have no idea.
It does JDBC to all the Scala standard types. That's the.
I have no idea. You could,
He uses like co-free and free, I think.
yes, which co-free and free, which are in some special form fixed points.
Okay.
And Rob Norris gave a talk about fixed point types and
I
Doobie.
didn't
And
understand that talk. I
yeah,
just wanted-
me neither.
Yeah.
It was too soon for me.
Okay.
But I'm not sure it uses recursion schemes explicitly in the macro realm.
Okay. But it's doing a similar.
But it's probably the same idea, yeah. So is everybody done with these two algebras and coalgebras? So if you're not done, please raise your hand. All right. Are you far from done or almost done? Oh, you're almost done.
I'm close.
Yeah, you're close.
But I didn't see the solution there, so I commented that out for now. I'll get it later.
Okay. So maybe we can move on to the test part. So who's familiar with at least the idea of property-based testing? Okay, so I still need to explain, because some of you are not. So property-based testing is basically the idea of generating random data and use that to test properties of your structures or functions. So for example, so you need two things. You need to find the invariants of your code, which are the properties, and you need to provide a way to generate random data for your data structure. So if you go to the file that's called Parquet spec, you will see one such property. It says that given any fix of schema F, if I use that to transform, if I use the algebra to transform to Parquet, and then use the coalgebra to transform back to schema F, I should end up with the same thing I started with. This is the kind of property you usually define when you use property-based testing. And so the whole trick is to be able to generate enough data that covers all the cases to make sure that your code is correct. You see, it's much more powerful than you come up with one example you write by hand and you verify properties on just that example, and so you forget the corner cases, and so you put bugs into production. But to do that, we need a way to generate arbitrary fix of schema F. And that brings us back to our exercise where we need to write this arbitrary. So again, arbitrary is a type class. And since schema F is recursive, to be able to write an arbitrary schema F, we will need an arbitrary schema F. So to break this loop, we use delay. And so now we just have to write a function that, given an arbitrary of A, will produce an arbitrary of schema F of A. So arbitrary is a Scala check class. And you basically use it like so. You write arbitrary. And here you have to put another Scala check class, which is called gen, for generator. So you have to provide a generator for schema F of A. And you have multiple combinators in the gen class. For example, you can say, I will produce one of, and there you put a list of alternatives. If you want to produce a constant thing, like for Boolean f, there is only one possible Boolean f. So I say gen.const Boolean f, gen.const integer f, and so on. And oh yeah, I have to ascribe that it's a Boolean f of what? Of A, yeah, yeah, of course, and so on and so forth.
You're right, this is an algebra.
That's a good question.
Or maybe it's called
Actually not. Because you're not going through a tree. There, we're not writing a function that takes a schema f of A and returns an A. We will see algebra in the next exercise. So.
Du délai qu'on a fait pour les courses, il y en a beaucoup qui n'ont pas vu pour les cordes.
On vient de le expliquer.
Oui, mais on n'y a pas fait
Oui,
ensemble.
oui, non, on l'a pas expliqué. Oui, t'as raison. Non, mais là, il faut qu'on accélère.
Bon, pas de souci. Juste que
So,
on n'a pas trop compris le délai.
Blah, blah, blah. How do we generate an arbitrary arrayf? Well, we need an arbitrary A. That's cool because we got one. So this A here is the arbitrary of A, right? It is an arbitrary, it's not a generator, but an arbitrary always contains a generator, which is called arbitrary, because otherwise people would have understood that it's a generator. So, yeah, naming things. And we can map over that to build an arrayf. Does that make sense? Because gen is a functor and it's also a monad. So we can chain multiple generators to build a more complex one. So for example, for structs, I will need a list of names for the field names, and then a list of schemas to map with these names, and I will be able to build a struct for that. So first, as someone said on the GitHub channel, you can generate a list of anything if you have the generator for this anything. But if you use gen.listOf, it will produce unbounded lists. So you might not want to produce structs that have 1,000 fields, because your test will run really long to run. So maybe we can say, let's first choose the size of the struct. So something between 1 and 10. So it's gen.choose. Then let's generate names, right? So it will be gen.list of n, and we will reuse the n we just generated. And it will be a list of strings. So we need gen.alpha string. So this will generate an alphanumeric string. So we have a list of names, schemas will be okay. And now we can yield a struct f of a list map of names.zip schemas and that should almost work. At least it compiles. Actually, the problem is Scala check generators, they try to go in every corner case possible. So basically, when you have a gen.alpha string, it will also generate the empty string, which might be problematic for later usage. And it will generate a list. So there is nothing that prevents two fields to have the same name. So we can probably be in trouble there. So we need to do something like that. To make sure we have distinct names. And so we cannot use n anymore, but we need to use the size of the list of names to make sure we have as much names as we have subschemas. And that should be it. Actually, we want to make sure. I know that you cannot know that yet, but we cannot use empty names for fields with Avro. So we want to prevent this generator to generate structs that have fields which name is the empty string. So a simple trick will be to add one character to each of the strings, so we are guaranteed that we do not produce empty names. So that should be something like something like that. That's pretty ugly, but that's the idea. We put an A in front of every names because we don't care about what the names are. We just care about the fact they are not the empty string. Okay, yeah?
Could we also just add a filter with a gen to filter out non-empty?
Yeah, completely. Yeah, you're right. That will be cleaner.
Does that affect the list of n that it produces? So like if it produces an empty string, will it produce one less than the list of n?
Actually, I don't know. I think it's I'm not sure about the filter function on gen, but I think if it filters everything, it will try again with a new seed or something like that. I'm not completely sure. So filter non-empty. Oh, no. Yeah, so this produces a list, and we want to filter that list.
I think it's map, or dot map,
So yeah, we can dot map,
and then underscore dot filter.
filter underscore dot non-empty dot distinct.
We have to do the dot distinct.
Yes, because we don't want to have two fields with the same name.
Oh, okay, okay. If I chain multiple maps, will Scallop use those? Will it do
No.
distinct? Okay. Their iterators, they will though. Thank you. You use the iterator first?
That's a mystery. All right, I suggest we take a quick break. Sorry, like 10 or 15 minutes. How are you feeling right now? Is it
Excited.
still okay?
Don't we have a break at 3 o'clock?
We can take the break.
There's like a break.
There's going to be desserts.
Oh yeah, okay. You know, it's in 15 minutes, so like you want, because after that we'll go on to the next part, which might become to feel a little bit more difficult. So I need you to be well rested and caffeinated and so on, because things are about to become less easy.
Next part, Avro or a validation?
Avro. And it might become more and more difficult as long as we.
Such a good CTO, worrying about your workers.
Yeah. All right, so it's not too bad if we take 15 minutes break, even if you slide a little bit after that. I will. If we start a new thing now, we'll miss the break. So it's. But if you have any question, I can stay there and answer questions.
Stay